Okay, Ma. So this is the problem which is given to you. Air at is it visible to everyone?
Oh, yes, sir. So, sir.
Yes, sir.
Air at a pressure of 20 degrees C and sorry, air at a temperature of 20 degrees C and at pressure of 1 bar is flowing over a flat plate at a velocity of 3 meters per second. If the flat plate is 1 meter wide and at 60 degrees C, calculate the following quantities at x equal to 280 mm. Okay, so the boundary layer thickness you are asked to find out. Okay, you can find out both thermal velocity boundary layer thickness as well as thermal boundary layer thickness, average friction coefficient, shear stress, and then average heat transfer coefficient, rate of heat transfer by convection, as well as total drag force up to x equal to 0.8. Okay, so this is what you are asked to find out. Okay, so now you are asked to find out del t average friction coefficient, cf x bar, okay, and then shear stress due to friction up to x equal to 0.8, okay, that is tau w. And uh, yeah, what is the other thing which is asked? Uh, what is the other thing asked? Yeah, rate of heat transfer by convection and total drag force up to x equal to 0.28 meters. So this is the question. Okay. Now, as I mentioned earlier, you are supposed to open the data book. Students, all of you, please bring the data book with you when you come to the campus. Uh, I hope most of the hostel students they have turned up by this time. Am I correct or not? Am I correct? Because in the afternoon also one of the student came and met me. I hope all of you have turned up. Am I correct? Am I audible?
Yes, sir. Audible.
Yes,
Sir.
sir. Audible.
Yeah.
Yes, sir.
What about the hostel students? Have you turned up to the campus or still you are there in your place? Yes. No hostlers were there. Only day scholars here. 37 students were there. No hostlers, in this? Okay.
Yeah, I guess most
So
of them are turned up, sir.
yes.
I guess most of them are turned up, sir.
Okay. Okay. Okay, Ma. So now what happens is you are supposed to find out the properties of air at full temperature. Okay. So this is very, very important. In the first problem, it is not mentioned. Okay. So first you have to evaluate the properties of air. Properties. Is it visible, Ma?
Yes, sir. Visible.
Properties of air at film temperature. Okay, so the film temperature is nothing but Ts plus T infinity Tf is film temperature, which is nothing but surface temperature plus fluid temperature divided by 2. So 20 degrees is the air temperature and 60 degrees C is the flat plate temperature. So 20 plus 60 divided by 2, that is 40 degrees. So at 40 degrees C, you have to take the data book, and in the data book, you have to go to the properties of dry air. I think it is in page number 33, I think. Am I correct, students? Properties of dry air. Where it is? Water, ammonia. All of you are there. All of you are listening.
Yes, sir.
Yes, sir.
Shall I,
Yes,
shall
sir.
I ask you to switch on the webcam? Do you? If you want me to do that, I will also do that. Okay, Ma. So at 40 degrees C, what is the density? Density is 1.128. Is it visible to you all,
Yes, sir.
Yes,
students?
sir.
So the density at 40 degrees is 1.128 kg per meter cube, and kinematic viscosity nu is 16.96 into 10 power minus 6. Prandtl number is 0.701, and K value. What is the K value? Tell me all these values, students. Density, how much it is?
1.128.
Density 1.128 kg per meter cube. And what about the second one? We want new value. Kinematic viscosity. Kinematic viscosity, how much it is? 16.96 into 10 power minus 6. And we need thermal conductivity value, Prandtl number and thermal conductivity. 16.96 into 10 power minus 6. What is the unit, ma? Tell me the unit.
Meter square by second.
Meter squared per second. Okay, meter squared per second. Okay, and what is the third one? We want K value. Is it correct?
Yes, sir.
The K value is
0.0275.
0.02756.
0.02756 watt per meter Kelvin, and the Prandtl number. Okay, Prandtl number is how much it is? 0.699. 0.699. Okay, now first we have to find out the Reynolds number. Reynolds number is equal to UL divided by nu. So here, or ux divided by nu, because at x equal to 0.828 mm we are asked to find out. Okay, at x equal to 0.28 meters, I'm sorry, not mm, 0.28. So what is the velocity of the air which is flowing? The velocity of air which flows is 3 meters per second. All of you are able to see this?
Yes,
U
sir.
equal to 3 meters per second. Okay, and x is 0.28. Now you can find out the Reynolds number. So Reynolds number is equal to ux divided by nu. So 3 into 0.28 divided by nu value. 3 into 0.28 divided by nu value, that is 16.96 into 10 power minus 6. How much it comes?
49,528.3. So 3019.
4.9 into 10 power
10 power 6.
10 power 6.
4.9 to 10 to the power 4, sir.
10 power 4. Okay, so which is lesser than 5 into 10 power 5. So up to x equal to 0.28. See, this is very, very important. The flow is laminar. The flow is laminar. Okay, I have already told you. So the flow may be fully turbulent, the flow may be laminar, or flow may be laminar turbulent combined. Now all of you, since we have found the flow is laminar, we can use the page number 113, ma. I don't know about your page numbers, ma. You will be having the latest data books, but in my so this is, you can see here 1.5.1 laminar turbulent combined. Okay, you should not use this formula to find out for this particular problem. Why it is so? Because this is laminar turbulent combined, and similarly you should not use you should not use uh fully where is that fully turbulent? There is one more thing which is fully turbulent from the edge, where it is laminar turbulent combined, constant wall temperature. I think one page is missing, because we have a combo of uh, yeah, 113, page number 113 is missing here. 112 and 114. So there is one more formula which is fully turbulent from the edge. Okay, so it is also there, but you have to find out, you have to use the laminar flow expressions. Okay, and I think any of you have the next page, ma? Can you just take a snapshot and put it in chat box? page number 113 or this next page. 112 is there, 114 is there. Any of you, can you please put that? Students? Students, all of you are listening or not?
Yes,
Yes,
sir.
sir.
1 minute.
Yes, sir.
Okay,
We
or
also have
otherwise I will do
this
one
box.
thing. I will take a photo shot and I will put it.
Sir, flat plate turbulent flow, sir. Fully turbulent from leading edge.
Let me take the photograph in the WhatsApp group.
Sir, I have sent it in Teams, sir.
Students, I have sent you. Students, in the WhatsApp group I have sent you, and yeah, I think one of the student has put it in chat box. Thank you. Thanks, ma. Thanks for it. Yeah. This is the one. So you can see here for fully turbulent from the edge. Okay, you have to, is it visible to everyone? Students?
Yes, sir.
Okay, for
Yes,
fully
sir.
turbulent from the edge, you have to use this del X formula, and Nusselt number you have to use this for average Nusselt number. You have to use this, and for laminar turbulent combined, you have to use this del Hx this formula. Okay, but here since we have got laminar flow, you can use this del Hx, which is equal to 5x into Reynolds number per x. Is it okay, students? This is very, very important. Okay, for laminar turbulent combined, it will be different. For fully turbulent from edge, it is different. Okay, students. For fully turbulent flow, it is different, and Nusselt number value will be different. Friction coefficient value will be different, and for laminar turbulent combined also it is different. Okay, so please understand that. And for this problem, only laminar flow. So you can use the first one, del Hx. Okay, so let me put it here and let me find it out. Del Hx, velocity boundary layer thickness 5x into Reynolds number per minus 0.5. Is it correct, students? Is it correct? Is it correct or not?
Yes, sir. Correct, sir.
What here? All of you are there, or you simply switched on and you went outside?
It's correct, sir.
Only one guy is saying. What about others? 4.9 into 10 power 4 whole power minus 0.5. So what is the hydrodynamic boundary layer thickness, ma? How much meters? Because we have substituted x in meters. Okay, Reynolds number is a dimensionless number. How much it is? Do it fast. Do it faster.
0.0063, sir.
0.0063.
63.
That is 6.3 mm.
Yes, sir.
Is it fine? Students, what about others? I hope around 50 students were there.
Yes, sir. Same, sir.
Yes, sir.
Same.
Sir, yes, sir. 6.32.
No one is
Into the power of-
answering here. Yeah, around 40 students were there. Okay, no one is answering. Okay, now del Tx. Del Tx, we know that it is del Hx Prandtl number per or minus 1 by 3. Okay, so del Tx, which is equal to del Hx into Prandtl number per minus 1 by 3 or minus 0.333, whatever it may be. Am I correct? Yeah. Now find out the thermal boundary layer thickness. Find out the thermal boundary layer thickness. Find it out more faster. How much meters? Prandtl number we know. We have already found it out. I have taken Prandtl number equal to 0.699. So 0.0063 into 0.699 whole power minus 1 by 3. How much it is?
0.007, sir.
0.007 meters, that is 7 mm. Is it okay, students?
Yes, sir.
Yes, sir.
All of you have taken down this?
Sure.
Okay, the next one is, yeah. So we have found out del Hx, we have found out del Tx. Okay, so velocity boundary layer thickness, thermal boundary layer thickness. All of you have taken down? Shall I move on to the next one?
Yes, sir.
Okay,
Yes.
ma. So the next one is, you are asked to find out, what is the thing you are asked to find out? Boundary layer thickness, average friction coefficient, shear stress. Okay, average friction coefficient, shear stress, heat transfer by convection, convective heat transfer coefficient, and drag force. So shear stress. Now, average friction coefficient is CFL up to length x 1.328 into Reynolds number per minus 0.5. So average friction coefficient, average friction coefficient, average friction coefficient is equal to, please tell me the formula, ma. How much it is? CFL bar, which is equal to 1.328. CFL bar, which is equal to 1.328 into Reynolds number per
Minus 0.5.
minus 0.5. Minus 0.5, is it correct?
Yes, sir.
Okay, ma. Now we know the Reynolds number is 4.9 into 10 power 4. Substitute it and get the result. So this is average friction coefficient. And after finding out the average friction coefficient, the next one is shear stress. Okay, shear stress is tau Wx, which is equal to Cfx, which is equal to tau Wx divided by rho u squared by 2. Which imply, what is the average friction coefficient, ma?
0.006.
0.006. Okay. There again, it is dimensionless. Okay, because Reynolds number is dimensionless. So average shear stress tau W will be equal to CFL bar into half into rho into u squared, u infinity squared. So 0.006 into half into density. So we have found the density from the data book, and velocity is 3 meters per second. Density is 1.128. Is it correct, students? Is it correct?
Yes, sir.
1.128 into 3 the whole squared. So average tau W value. Tau W. So what is the value? Tau W. How much Newton per meter squared? How much might is?
0.03.
0.03.
0.
0.03.
0.03 Newton per meter squared. Is it correct, students? Everyone? All of you are getting it?
So
Yes, sir.
yes, sir.
Okay, ma. And so we have found out average shear stress. So average shear stress equal to this. Now the next one, what is asked? Heat transfer. So to find out the heat transfer, we have to find out the average H bar. We know that Nusselt number average, which is equal to H bar L by K. Okay. Now average Nusselt number is also equal to, for laminar flow, average Nusselt number is equal to, you can see this slide. So for laminar flow, average Nusselt number is equal to 2 times of local Nusselt number. Okay, average Nusselt number is equal to 2 times of local Nusselt number. I think it is here also there. No, it's not there. So average Nusselt number is equal to 2 times of local Nusselt number. So you can use this expression. If the Prandtl number is in between 0.6 to 0.6 to 50, for constant wall temperature problems, the local Nusselt number is 0.332, Reynolds number per 0.5, Prandtl number per 1 by 3. So that formula you can use. Okay. So the average Nusselt number is 2 times of Nu local. Okay. So 2 into 0.332 into what is the value? Reynolds number per 0.5, Prandtl number per 0.33. Reynolds number per 0.5. Please correct me if I am wrong. Is it correct?
Yes, sir.
Okay, ma. Now substitute and get the result. Average Nusselt number. 2 into 0.332 into Reynolds number. What is the Reynolds number, ma? 4 into 10 power 4. How much we got? 4.9 into 10 power 4. 4.9 into 10 power 4 into Prandtl number. What is the Prandtl number we got? 0.699. Approximately 0.7. Find it out fast. What is the average Nusselt number? Nu bar? Find it out faster. All of you are there doing the calculation? Achyutan? Are you there?
So calculating, sir.
The 0.00258.
0.00?
258.
0.00258. Please check it. Is it correct?
So I'm getting 28,875.
What year?
Yes, sir. It is 28,000, sir.
28,000.
Sir, yes, sir, 28,000, sir.
Please check the calculations properly, ma. 28,000. Nusselt number. Please tell me the answer.
28,875, sir.
289.
28875, sir.
Okay, ma.
875.08.
28875.08.
08.
So nu bar. We also know that average Nusselt number is equal to h bar L by K. So which implies h bar is equal to nu bar into K divided by L. Okay, so that's why we have found the thermal conductivity value also. So thermal conductivity value is 0.02756. Okay, we have already calculated at the beginning. So substitute that and get the result.
Hello, sir.
Yeah, anything?
Yes, sir. So actually, the average Nusselt number value I'm getting is 130.5, but I think the 4.9 into 10
Yes,
power
sir, it's
5
138.
Yes, ma.
0.5.
I have missed it.
130.
I'm sorry, ma. The whole power 0.5. I missed it here.
So it should
I
be
have written the formula
130.5.
Sir, it's
correctly.
130.
Reynolds number power 0.5.
Yes, sir, it's 130.444.
Oh, yeah. Okay, ma. I'm sorry for that. I did the mistake there. In the formula, I did Reynolds number power 0.5. Here, I didn't write that 0.5. Yeah. What is the number, ma? Now you can say
130.4.
130 point.
130.4.
0.4 or 0.5. sir.
Is it
Yeah.
correct?
Yes, sir.
Okay, ma. I did the mistake there. 4.9 into 10 power 4 whole power 0.5. Students, is it correct, students?
Yes, sir.
Yes, sir.
Okay, ma. Now 130.4 into the K value. K value we got it here as 0.02756. 0.02756 divided by L. L is nothing but X, which is nothing but 0.28. So find out H bar. How much H bar will be? Nu bar K by L. 130.4. All of you please check you are getting 130.4. 130.4 into K value
Sir,
0.02756 divided by 0.28.
12.8390.
12.839 watt per meter squared Kelvin. All of you are getting it, ma? H value?
Yes, sir.
Yes, sir.
Yes, sir. Same one.
Okay, ma. So 12.839. Very good. Sorry for this. Reynolds number power 0.5. I missed it out here. 4.9 into 10 power 4. Please check it and do it. Okay, ma. Now find out the heat transferred from one side of the plate. So the heat transferred. What is the width? Width is 1 meter. That is what mentioned in the question. Am I correct? Width is 1 meter. If the plate is 1 meter wide, okay. So the width is 1 meter. Now Q, which is equal to H bar into area into del T for one side of the plate. Is it okay, students? For both the sides, 2 into A. That's it. So H bar. What is the H bar value we got? 12.
So 12.38, sir.
12.3839. I'm sorry. Is it 12.839?
Yes, sir. Yes, sir.
Yes, sir.
Yes, sir.
12.839 into area, 1 meter into 0.28. If both the sides were asked, then you have to multiply it into 2 into del T. Del T is 60 minus 20. Am I correct, students? Because the surface plate is at 60 degrees, plate it is 60 degrees and air is at 20 degrees. Is it fine? So how much watts? The answer? How much watts, ma? This is in watt per meter squared Kelvin. Meter squared gets cancelled. This is the temperature difference. Temperature difference.
143.79, sir.
How much?
143.7968.
Watts. Okay, this is the final answer. This is the heat transferred, and finally total drag force. Total drag force total drag force. I have given you the formula in the morning class. What it is? Drag force, which is equal to shear stress into area of the plate. Am I correct? Am I correct, students? Shear stress into area. Am I correct or not?
Yes, sir.
Yes, sir.
So now we know the tau W. We have found it in the first slide. What is tau W? Tau W is 0.03 Newton per meter squared. 0.03 Newton per meter squared. See, you have to do it faster, ma. Into area 1 into 0.28. How much newtons?
So 0.0084.
0.0.
84, sir.
Is it correct? All of you?
Yes, sir.
Yeah. Okay, ma. Like this, you have to solve. Is it fine, students? So we have found out the heat transferred by finding out h bar. H bar we have found out with the help of Nusselt number. So average Nusselt number is 2 times of local Nusselt number, 2 into 0.332, and we found this. Okay, and then we found this. Okay, we have found the hydrodynamic boundary layer thickness, that is velocity boundary layer thickness, thermal boundary layer thickness, friction coefficient, shear stress, and we have found out Nusselt number, and we have found out the h bar, convective heat transfer coefficient, average convective heat transfer coefficient, and we have found everything. Okay, is it okay, ma? All of you have taken down? All of you?
Yes, sir.
Shall I
Yes.
move on to
Yes,
the
sir.
next one? Shall I move on to the next one, ma?
Yes, sir.
Yes, sir.
Okay. Uh, the next problem is this one. Okay, first off, I will do it. Second off, you have to do it, and you have to show it to me when you come on Thursday. Is it okay? One portion I will show. I will do it, ma. Is it okay, students?
Yes, sir.
Yes, sir.
Okay, ma. Now, what happens here is air at 10 degrees C and velocity is given 75 meters per second, flows over a flat plate of a dimension 450 mm by 600 mm. The plate is maintained at 90 degrees C. Determine the drag force experienced on both sides, heat transfer rate and critical length. Okay, what will be the effect if the flow is parallel to 600 mm side? Okay, so first we have to assume that the flow is over 450 mm side. Okay, so you have a flat plate. Students, all of you please listen. You have a flat plate. I don't know about students, this is 450 mm and this is 600 mm. Is it okay, ma? Is it okay?
Yes, sir.
Yes, sir.
So in the first case, the air is flowing over the 450 mm side. Okay, and in the second case, in the second case, the air is flowing in this direction towards the 600 mm side. So this will be 600 mm. Okay, and this is 450 mm. Okay, students? Okay? Students,
Okay,
is it okay, ma?
Yes, sir.
So first I will be solving this. The same procedure you adapt for the flow across 600 mm side. Okay. flow across 600 mm side. Is it fine?
Yes, sir.
Yes, sir.
Okay, ma. So you are asked to find out what is the critical length. Okay. So the critical length is the length at which the Reynolds number is equal to critical Reynolds number, RE critical, which is equal to 5 into 10 power 5. Am I correct, ma? Am I correct?
Yes, sir.
Okay. So we know that RE, which is equal to UL divided by nu, or L critical will be equal to RE critical into nu divided by U. Am I correct or not? Am I correct, ma?
Yes, sir.
Critical Reynolds number is 5 into 10 power 5. Okay. So up to this value, the flow will be laminar and then it will be turbulent. Okay. Now, let us find out what is the film temperature here. Air temperature is 10 degrees C and plate is maintained at 90 degrees C. Okay. So you have to find out the critical Reynolds, film temperature first. T film, which is equal to Ts plus T infinity by 2. What is the surface temperature? 90 degrees C. Plate temperature 10 degrees C. So the film temperature is 50 degrees C. What is the fluid, ma? What is the fluid? Students, please tell it here. All of you are interested or not? Hello?
Yes,
Am I
sir.
audible?
Yes, sir.
Yes, sir, audible.
Guys, next week you will be coming to the classroom. I will make sure that how many of you are writing it. Let me see. So surface temperature is 90, air temperature is 10. Ts equal to 90, T infinity equal to 10. So the film temperature is 90 plus 10 by 2, 50 degrees C. So again the air is the fluid. Again you go back to page number 33 and in page number 33 you have to find properties of air at 50 degrees C. Is it right? And this is the property of air, right? 50 degrees C.
Yes, sir.
Is it visible to you all?
Yes, sir.
Okay, man. Now tell me the values: density, viscosity, nu value, K value, Prandtl number value. Tell me the 4 values. What is density?
1.093, sir.
1.093 kg per meter cube. Viscosity nu. Please do it faster.
17.95 into 10 to the power minus 6.
17.95 into 10 power minus 6. Okay, K value.
0.02826.
0.02826 and Prandtl number is 0.698. Is it correct?
Yes, sir.
Yes, sir.
Prandtl number is 0.698 and K value, how much it is?
0.02826.
0.02826. Okay, ma, watt per meter Kelvin. Okay, units are also important. Okay, so these values we find out. Okay, now what is the velocity of flow? The velocity of flow is 75 meters per second. Okay, first we are finding out for 450 mm side, 600 mm side, you have to do it. Now, critical length, L critical, which is equal to RE critical into Reynolds number is UL divided by nu into nu value divided by UL divided by nu U. Okay, so 5 into 10 power 5 into nu value 17.95 into 10 power minus 6 divided by how much it is? U value 75. What is the length, ma? What is the critical length?
Sub 0.1197.
Point
0.1197, sir.
1197. Okay, so 119.7 mm. It is up to which it is laminar. Okay, so out of this, students, out of this 450 mm, out of this 450 mm up to 119 mm. Okay, up to 119 mm, it is laminar, and remaining it is turbulent. Okay, so what you have to do is you have to look into the formula for laminar turbulent combined. Okay, you should look into the formula for laminar turbulent combined. This is fully turbulent. For laminar turbulent combined, this is the value. Okay, I think I have it in my data book. Yeah, is it visible, Ma? Is it
Yes, sir.
visible?
Yes,
Yes,
Okay,
sir.
Ma. Okay, so what is the Prandtl number? The Prandtl number is in between 0.6 to 60. Okay, and Reynolds number, we have to find out up to the total length L, and we can use this Nusselt number formula. This general expression we can use to find out average Nusselt number. Nu bar as NUL bar as average Nusselt number. But before that, we are expected to find out the uh, friction coefficient, average friction coefficient. After getting the average friction coefficient only, we will be able to find out tau W or average shear stress. It is asked right in the question. Drag force is asked. Okay, so what is the drag force formula? Drag force formula is shear stress into area. So to get the shear stress tau W, we have to find out the friction coefficient. Okay, so many things were asked in this problem. Is it correct, students? Am I correct?
Yes, sir.
Yes, sir.
Okay, let me take the next. See, now you can first find out Reynolds number up to total length L, REL, which is equal to UL divided by nu. 75 into the total length. Total length is 450 mm, right? Am I correct?
Yes, sir.
And what is the new value? Please tell me faster.
17.95.
17.95 into
10 power minus 6.
10 power minus 6. Okay. So how much the Reynolds number? Up to the total length of 450 mm. Find it out faster.
The 1.88 into 10 power 6.
Up to 450 mm. How much it is?
1.88 into 10 power 6.
1.88 into 10 power 6. Okay, again, it is greater than 5 into 10 power 5. So it is laminar turbulent combined, this formula. Okay, so we should not use it as laminar flow. So we are using this laminar turbulent combined formula. Okay, so now here for average friction coefficient up to length L, we can use this general expression. Okay, so this expression we can use, or this also you can use. Okay, but let us use this CFL, this value. Okay, so you may not say it is local. Okay, so in the data book itself, for laminar turbulent combined, CFL is mentioned as average friction coefficient, and it is 0.074. So CFL is equal to 0.074. Can you please read it out? Reynolds number per minus 0.2 minus 1742. Reynolds number minus 0.2 minus, what is the value, ma? Say, what is the expression, ma? 1742, 1742 into Reynolds number per minus minus 1, na? 1 or
1, sir, -1.
yeah.
Yes, sir, -1.
Okay, ma. Now substitute and get average value. 1.88 into 10 power 6 whole power minus 0.2 minus 1742 into the same thing. Sorry, 10 power 6 whole power minus 1. How much it is? Average friction coefficient and tau W average is equal to CFL into half into rho U infinity squared. Is it correct, students? The formula? Yeah. What is CFL value, ma? Please tell me faster. Time is running out.
3.188 into 10 power minus 3.
How much it is? Louder?
3.188.
0.0032.
0.0038. Check the values, ma.
0.0031, sir. 318.
0.00318.
Sir, 318.
Is it correct?
Yes, sir.
Okay, into half into density. What is the density we got? Density is 1.093 and the velocity is 75. 1.093 into 75 whole squared. So how much might is? It will be in Newton per meter squared, right? Shear stress.
9.775, sir.
9.775
775.
Newton per meter squared. See, I'm not looking into the textbook values, ma. After solving only, I have to find out. Now, what is the drag force, ma? Formula? Drag force is? I have given you in the last problem.
Shear stress into use.
Shear stress into area. Is it correct?
Yes, sir.
So shear stress into area. Area on one side. So 9.775 into area. So area, what is the dimension of the plate, ma? 600 mm by 450 mm. Am I correct, students?
Yes, sir.
450 by 600. So 0.45 into 0.6.
So they've asked for both areas, sir.
Both the sides, huh?
Yes, sir, both sides.
What will be? Yeah, drag force on both the sides. Okay, into 2, ma. So into 2. Area into 2. Both sides. Students, some of the students, they will be doing the mistake here. So please understand, if both sides is asked, so you have to multiply the area into 2. So how much it is? Drag force? Please do it faster. And after this, we have to find out
5.2785.
5 point.
2785.
Is it correct, students?
Yes, sir.
Yes, sir.
Newtons. Okay. So we have found this. Now, what is the next one asked? The next one is heat transfer rate and critical length we have found out. The last one is heat transfer rate. Okay, it's so simple. So heat transfer rate, heat transfer is Q equal to HA del T for one side. If we consider two sides, 2 into H into A into del T. So, which is nothing but H bar, average value. So, H bar, which is equal to NU bar HL by K. HL by K equal to NU. So, NU bar into K divided by L. Okay, so this is the thing. Okay, now you have to find out NU bar. So NU bar which is equal to for laminar turbulent combined CFL is, see, this is the formula. Prandtl number per, this is general expression you can use. Prandtl number per 1 by 3. This is visible to you, students. Am I correct?
Yes, sir.
Students?
Yes, sir.
NU bar which is equal to, please tell me the formula, my expression.
Prandtl number 0.33.
1 by 3 into
0.037.
Yeah, into 0.037 Reynolds number per 0.8 minus 871. 0.037 Reynolds number per 0.8. How much it is?
Yes, sir. 0.8.
Reynolds number per 0.8 minus 871. Minus 871. Okay. Now the Prandtl number, we have found it in the very first beginning itself. We have found it. How much the Prandtl number? The Prandtl number is 0.698. Okay, ma. Please tell me the values faster. 0.698. What is the Reynolds number we have found out? Up to total length. What is the Reynolds number we have found out, ma? What you are, all of you are sleeping,
The 1.88 into 10 power 6.
1.88 into 10 power 6.
So
See,
1.88.
I am going back and I am seeing all the values, ma. I don't know. 1.88 into 10 power 6 minus whole power 0.8. Please don't miss it. Minus 871. So what is the average Nusselt number?
So 33,546.06.
Is it correct? Is it correct, students? Please check it.
So I'm getting 2,658.84.
What year?
Yes, sir. 2658.
2600,
2,658.84, sir.
2658.4. What about others here?
Same, sir.
Only 3 members were saying
Same, sir. So same,
2000.
2600 and
58.84, sir.
Okay. Now NU bar which is equal to H bar L by K. Okay. Now we can find out what is H bar. H bar is equal to NU bar into K divided by L. So 2658.84. K value ma, thermal conductivity. First page.
0.02826.
0.02826. Okay. And length is 450 mm, right? So you have to do the same procedure for 600 mm. So the Reynolds number will be different for 600 mm. Is it okay, students?
Yes, sir.
Okay, ma. What is the average Nusselt number, ma? We have come to the
166.
conclusion. How much it is?
166.97, sir.
166.97. Again, dimensionless number. Now Q equal to Sorry, this is H bar, right? I'm sorry. This is H bar,
Yes, sir.
watt per meter squared Kelvin. Nusselt number is 2658.84. Nusselt number into thermal conductivity divided by length. So Q equal to H bar into 2 times of area because both the sides into del T. So 166.97 into 2 into 0.45 into 0.6 into Ts minus T infinity. 90 minus 10 nama.
Yes, sir.
Del T is, see, please take a note, del T is Ts minus T infinity. Surface temperature minus fluid temperature. So how much it is? So this is the final answer. The time is 7:30. As I promised you, I did to
7213.2.
7213.132.
0.32, sir.
0.32
0.32, sir.
watts. So this is the final answer.
7
Students,
to 1.
all 7213. I'm sorry. 7213. Yeah.
Yes, sir.
Okay. Students, now all of you are able to understand. Now, what is the difference between the 450 mm side and 600 mm side? Only this Reynolds number changes. Remaining other things remain the same. All the other steps remain the same. CFL values changes because Reynolds number changes. Okay, Reynolds number will become more because a critical Reynolds number is going to be the same, like 119.7. Okay, but the Reynolds number changes because in the place of 0.45, it becomes 0.6. So you will be getting increased value when compared to 1.88 into 2 and 10 power 6. You will be having increased value here, and you will be having more value for shear stress and more value for drag force. And similarly, you will be having more value for convective heat transfer coefficient, Nusselt number, as well as convective heat transfer coefficient and heat transferred. Okay, on the 450 mm side, it is 7000 watts, and on the 600 mm side, it will be slightly higher. Is it fine, students?
Yes, sir.
Yes, sir.
Okay, shall I stop with this? I'm sorry for troubling you, ma, because see, if I keep on dragging it till the last minute, it won't be proper.